Hi, welcome to this video in which we'll talk about the first of our floor systems, this being the one-way slab system. Now, one-way slabs, right, are a common system that is typically found in warehouses, right, and then commercial and residential construction, right. You see it sometimes in some industrial buildings, and then sometimes it's pure concrete. Sometimes you find it also used together with steel, right? With steel, and this is how it looks like, right? This is how it looks like. So in this particular case, right, you have this, right, and then you can see the right. Most likely you can see here that this roof system is made up by beams, right? Kind of what we'll call beams, right? So segments that span from side to side, right? And then the one-way system is, right, or it's termed like that because the load, right, travels in one direction, right, mostly. So that is why it's called one-way slab design, right? So in this particular case, right, so we have it. It's the composite steel concrete one-way slab, right? Same principle again, right? Now this is not divided into segments, but the load travels to, right, predominantly in only one direction, right? In only one direction, and then this system uses the beams, right, to unload the forces, right? So this is the action of one-way slab, right? Now, so this type of slab, right, the one-way slab system, is very common in building construction, right? You rarely go a day without walking on a slab, right? And then we will see later that there is one-way slabs and then two-way slabs, right? But this type of floor system is quite common, right? Now, this distinction between one-way and two-way, right, depends on how the load is distributed along them, right? And then we were just talking a little bit about this in the previous slide. Now, we have to realize, right, that the floor system is just a way, right? It's part of the loading path, right? Now, loading path, all the loads that a building experiences, right, they have to be transmitted somehow back to the foundation, right? So very typically, right? Very typically, let's say if you consider an apartment building or an office building, you have people and furniture and equipment there. So all those weights are going to be transferred first to the slab, right? Not to the beams, but to the slab. Then the slab, right? From the slab, right? Let me just from the slab, you go to the beams, right? Then the beams connecting to columns, right? And then columns floor to floor down all the way to the foundation, right? Now, so far we have only done beams and columns. So if we learn, or when we learn slabs in this topic, right, either the one-way or the two-way, right, you will be well on your way to to design your building, because we'll do foundations later in this course, right, later in this term. And the only thing that you will have for a future course, right, basically, right, in terms of basic components, is walls, right? But walls, rather than a kind of a load path, right, or having to play a role into how the loads get down from the floors into the foundation, the walls, right, they provide stiffness, right? So provide stiffness. They are the so-called lateral load resisting system, right? They provide stiffness and strength against lateral loading, right? But doing slabs today will get you on your way to become those proficient structural engineers you want to become, right? So on the one-way slab components, right, it's very typical to use a one-way, right, one meter design width, right? So we design strips, right, rather than just designing the whole thing. We just go 1 meter by 1 meter, right? And then, right, if everybody we make it clear that we design just 1 meter of the slab, right? It doesn't matter that you have a 100 meter wide right, 100-meter wide slab, right? You are designing only 1 meter strip, and then that design can be transferred to the rest of the slab, right? So in this particular system, right, the one that we see here, the slab is supported into beams, right? Supported into beams, and then we call these beams, right, or spandrel beams, right? If they are the big elements that support other beams, right, they are called as spandrel beams, right? Now, if you take a look, right, if you take a look here, right, at this part of the figure, right, you will see that one-way slabs, right, one-way slabs often are the flanges of T-beams, right? You see your T-beam over here, right? So that flange in the other direction, right, was the one-way slab, right? All what we have been doing is taking a look at this beam from this side, right? So we were looking at it from this side, and then all we saw was a T-beam, and we designed it in this way, right? So we designed it, right? But the loads on that T-beam, right, they were coming from the one-way slab, right? From the one-way slab that T-beam was carrying, right? And where was that T-beam? Well, it was the flange of the T-beam. So, right, don't get surprised if you have to design, right? For example, in this case, you'll have to design the one-way slab, right? And we will see that that involves placing steel and other structural considerations, right? You design this slab, right, and then you design the beams, right, and then these T-beams, they have to because those loads don't disappear, right? You say, well, the loads are being taken by the slab, by the one-way slab. Well, and who carries, right? Who supports the one-way slab? Well, the T-beams, and now they have to be designed, right, for the loads that are tributary to each T-beam, right? So first the slab, right? Design the slab, then design the T-beams, right? Get that force down, right? Get that force down. So the main difference, right? The main difference between one-way and two-way slabs, right? Imagine you have this system here, and it is supported, maybe beams, maybe, right, other structural elements. So let me just make it clear that I'm drawing here kind of a support, right? So this is supported onto something, right? It may be two T-beams, right, that go along, right? And then, right, what we have here is that the overwhelming majority of the force moves in one direction, right? In this case, illustrated here is this direction. Now, so how do we know, right, which direction the force moves? Well, you have conservation of energy, right, in nature. So the one way of looking at this, right, far from the mathematical and physical definition, is that nature is lazy, right? It will want to find the shortest path, right, to do something, right, the minimum amount of work. Now, all this load present on this slab, right, the shortest path, right, the shortest path to the supports, right, is if the load, right, if the load goes, right, to the supports by the shortest path, right, and then you would see, right, you would see that all this load moves to the support as quickly as it can. So it's going to choose the shortest path, right, and then in a kind of a graphical way, you would see that these loads moves into this direction rather than into the other direction, right? So negligible amount of force moves in the other direction. Now, this helps us visualize that if we have a case in which the shortest path is kind of not clear, right? So we're talking about squarish slabs, right? Then we can see some load going into this direction and some other load going maybe into the other direction, right? So force move, right? It's more evenly split in both directions, right? Now, in this case, right, and you will see, still most of the load moves into one direction predominantly, right? So these forces will be bigger, right, than in the other direction, but you still have that kind of sharing, load sharing, right? So a way to define, right, one-way and two-way action is in terms of the dimensions. You see A here, right? A here in the long direction, B is the short, right? A is still here, B is still here. The short A the long, B the short direction. So if A over B is bigger than 2, right, you have one-way action. And if A over B is less than 2, then you will have two-way action, right? Two-way action. So it's an easy way to define what's going on with the law, right? You can have precast one-way slab systems in which you get these right, you get your slab as beams actually, and then you connect them together on site, right? You get them together inside. So this one-way or two-way slab behavior, it's not just particular from concrete. You can have it in steel, right? Right, you see the beams. So the load goes from one direction predominantly like this, right? You can have it like that. You see them everywhere, right? You see them everywhere. Car parks, right? Parking garages are also a very very typical location for one-way slabs to be located. Right? Now, if the loads move in one direction, right, then you may say, or you may ask, right, what's the difference between a one-way slab and a beam? Because in the beam, right, in the beam, you load it, right, you load it, and then, right, and then you could say, well, the same one-way action happens when I, my 3D drawing is not good, right, because, right, you have this tension here and this compression here, right, still all the forces traveling in one way, right? So you could say, or you could see that one-way slabs and beams are very, very similar, right? And you are quite correct. Now, one-way slabs, right, can be seen as, right, one-way slabs can be seen as wide, right, shallow, right, shallow, not too deep, right? One-way slabs are can be seen as wide, shallow, rectangular beams, right? So this is a beam, and this is a slab, right? It's kind of more flattened, right? Kind of more flattened. So this is just a cut of a slab, right? So cut of a slab. So differences, right? Now slabs are going to be typically designed as 1 meter wide elements, right? Usually, right? Slabs, right, usually don't have stirrups, right? Slabs don't usually have stirrups. The stirrups, remember, right? They look like this. Oh, right? And then slabs don't have stirrups. Well, why would a slab not have stirrups? Well, there is just not enough space, right? There is not enough depth to place stirrups economically. Also anchoring those stirrups, right, will be challenging, right? So essentially, or usually, right, this dimension, right, in a one-way slab maybe, right, 120, 170 mils, right, maybe 200 mils at most, right? So getting a stirrup, right, so how do you put it, right, like this, right? So this is going to be very hard to make, right? This is with the cover and the dimensions of the bars, this is going to be maybe 100 mils, right? Less than that, 80 mils, right? So making those bends on the stirrup, right, it's going to be challenging, right? And then you have to place many, right? And then you have to place many stirrups, right? And then placing those many stirrups may not be economical or even impossible when you are building the actual slab, right? So in slabs, right, in slabs we typically don't have stirrups. We have other sort of steel hardware that we can use when the sheet is really, really big, but usually we are going to rely on the concrete contribution alone to carry shear, right? So we are not going to be depending on stirrups or any other steel reinforcement, right? In most of the slab to carry shear forces, right? Now, when we have very high shear forces near the supports, sometimes we use a different type of reinforcement, right? But it's not going to be the focus at this point. So slabs, right? Slabs will have transverse reinforcement, right, for temperature and shrinkage control, right? we are going to prevent excessive cracking in our slabs, right? If we put our transverse steel. So imagine you have a 1 meter wide strip of slab, right? So this is what the 1 meter, my 1 meter strip design, and then you see this. This is the longitudinal reinforcement. This is what we are going to learn how to place, right? This steel goes in the direction of the loads, right? But you see this bar? This red line is a rebar, right? That goes in the transverse direction. Well, that is intended to take temperature and shrinkage, right? Shrinkage is when the concrete loses water and dehydrates and then starts shrinking, and then if you restrain it, right, that shrinkage may cause cracking. So those transverse bars intend to minimize that temperature and shrinkage strains that may crack your one-way slab badly, right? So in continuous structures, right, or when you pour your slab with your column system in your beam system, you are going to end up with a continuous, right, with a continuous structure, right? Your one-way slab is going to be connected to columns and beams, right? So these are cast in place, right? Cast in place concrete structures, right? In which you put everything at once, right? So you end up having a continuous structure, right? So it is a good time to introduce continuous beam design, right? You can have this sort of system, right? As opposed to some precast systems in which I think we were talking about that earlier, right? In which you leave this sort of element, right, called corbels, right? This is precast construction, right? So this is just a cut, right? So your columns are prepared with these so-called corbels, but then you see that they seem like a support, right? And then all you have to do is to go to the precaster and then order a beam, right? A precast beam, and then you just come and sit it like this, right? So this system, you end up with a bunch of simply supported beams, right? A bunch of simply supported beams, separate from each other. But in this system, right, you are going to have what you have learned now to recognize as a continuous system, right? This is the difference between one and the other, right? So for the continuous system, right, because designing a simply supported element, right, the beam is statically determined, right? You know that the moment is WL squared divided by 8, right? That is the maximum moment. The shear, right, WL over 2 and WL over 2, right? But how do the moments and shears look like for a continuous structure, right? Now you may remember from the handout you were given how to get that moment and shear in continuous structure, right? So you may remember that the moment, right, may look like this, right? That's how the moment may look like, right? That's how the moment may look like. And then the shear, right? The shear, right? Of course, I'm putting moment and shear in the same plot. The units don't matter, right? So that's how they look, right? That's how they look, and it becomes a bit more complex to obtain continuous moments and continuous shears for this structure, right? Now the benefit of having a continuous structure, right? Now we just saw that it is a bit more difficult, right? A bit more difficult to obtain, right? To obtain moment and shear in continuous structure, right? But they have many benefits, right? Many benefits, and you have to kind of balance the two, right? So where will you have your steel, right? Let's say for flexure, right? For flexure, so positive moment, right, and negative moments, positive moment, negative moments, positive moment, negative moment, positive moment, negative moment, right? So having a continuous structure will require you to think about where to get that steel, right? And then remember, we're going to link this topic later with cutoffs, right? We'll be doing all the cutoffs for this beam. Not really, right? We are going to follow some rules, right, about how to do the cutoffs in an easy way for a continuous structure. So the benefits of having a continuous structure is that it's going to be easy to build, right? Less joints. The weakest part of a structure is the joint, right? So having less joints to detail and to take care of is going to be quite effective, right? Quite cost effective, right? We're going to reduce maximum moment magnitudes, right? The moment in a simply supported element is WL squared divided by 8. Let's just do the easiest thing, right? You may remember that the moment here is like this, right? Now, in terms of total moment, you have the same, right? WL squared divided by 8, and then this is equal, right? The total moment, right? Positive plus negative is WL squared divided by 8. This is just due to statics, right? That's known as the static moment. But then you have here, right? WL squared divided by 12, WL squared divided by 12. And here we have WL squared divided by 24, right? So the total moment that you have to carry, right? The total moment, positive or negative, right, is less. WL squared divided by 8 is bigger than WL squared divided by 12. Right? And much bigger than WL squared divided by 24. So you reduce the maximum moment magnitudes, right? And if you reduce the moments, right, you have reduced deflections, right? You can make members thinner while still satisfying deflection limits, right? And you add redundancy and also capacity, right? Redundancy because, whenever you have more points of distribution of load, right? If you have a continuous system, then maybe if you in one span you are carrying too much load, right, more than you designed, the adjacent spans, and this is what I mean, right? So this span is carrying a lot more load that it was designed to carry. Well, this span and this span, right, are going to help that span carry the load, right? And sometimes the load, right, even less, that is going to be transferred into other spans, right? So that is redundancy. And capacity, because, right, if all the spans are going to help each other, right, you can get some benefit of adding capacities, right, from span to span, right? So, well, let's use continuous structures, right, all the way, right? From this point on, it will be just continuous structures in your future. Well, some drawbacks, right? The analysis is going to be a bit more difficult, because it's going to be, you are going to have a bunch of statically indeterminate, right, structures, right? So, or one statically indeterminate to many degrees structure, right? Just one, but it's going to be not easy to get that moment of WL squared divided by 8, or even that, WL squared divided by 12 here, right? So we know those values by memory, right, or off memory. But what is the moment for a 10 span beam, right? So that's a bit more difficult to get, right? And then you have to use load combinations, right? So it's just not only one load scenario, but many, and then it quickly becomes quite interesting, right? So you have one beam which is continuous, and the building may have many, right? So buildings can be indeterminate to hundreds of degrees, right? So you will have many moment resisting connections, right? Every connection between beams and columns and supports are going to be right, indeterminate, right? So it's not going to be easy to find the moment there, right? So if you are going to be doing this analysis, right, you have also to account for the stiffness of the connecting beams and columns, right, to get your moment. So instead of a simply supported member, which right, the moment it's independent from the supports, because these are intended to be simple supports, now you have to you have to account for the stiffness of the supporting beam and columns, right? So right, you saw a bit of that in 372, right? And then in simply supported elements, right, you just deal with the positive moment. But in continuous structures, you are going to have to deal with positive and moment. Positive and negative moments, right? Positive and negative moments. So, so this is how kind of the first introduction of what one-way slabs look like. And then the next video, right, is going to be about the detailed requirements. We'll see where the steel goes and why, how to choose the thickness, right, how to choose the clear cover. We'll do a review on how to get the moments and shears in continuous one-way slabs. We'll discuss cutoff locations, right? We'll talk about the reinforcement that goes in the transverse direction. We'll talk about how to choose the bars, right? And how spaced they have to be, right? Minimum and maximum spacings. And yeah, after that, we will find out how to design for flexure and shear, which will be thankfully very similar to what we did in beams, right? In beams. So thank you very much and see you in the next video.